In the last lesson, we used a water circuit as an analogy to an electric circuit. Now I have an electrical circuit with a battery and two resistors in series. The battery, just like the pump in the water circuit, pumps charged particles throughout the circuit. The wires are like the clear tubes. They provide very little resistance to the flow of charged particles. These resistors are just like the mesh tubes. They provide resistance to the flow of charged particles, just like the mesh tubes provided resistance to the flow of water in our water circuit. I also have an ammeter, which can measure the flow of charged particles through the circuit. So let's connect the ammeter at various points in the circuit and see how the current changes. We'll compare our observations with our observations in the water circuit. When I place the ammeter before the two resistors, I get 15.04 milliamps. Now I'll put the ammeter in between the two resistors. I've put the ammeter in between the two resistors. It now reads 15.04 milliamps. Now I'll move it to after both resistors. When I place the ammeter after both resistors, it reads 15.05 milliamps. As you can see from our three readings, the current when resistors are connected in series is the same. So this is consistent with our observations from the water circuit. It's also consistent with the law of conservation of charge. So the charge didn't disappear and we didn't have charge created out of nowhere. It stayed the same. Now that we've seen that current is the same everywhere in a series circuit, let's look at Kirchhoff's loop rule. Kirchhoff's loop rule states that the sum of potential differences around a closed loop in a circuit must be zero. So let's look at a circuit with a 6-volt battery and two resistors in series. One resistor has a resistance of 105 ohms, and another resistor has a resistance of 305 ohms. We're going to follow the path of a charged particle throughout the circuit and look at the change in electric potential. Remember that conventional current is the flow of positive charge. We know that they're actually electrons flowing through the wires, but due to historical reasons, we use conventional current as the flow of positive charge. First, we need to calculate the current leaving the battery. By adding the resistance of the two resistors in series, we can find the total resistance in the circuit. So that would give us 410 ohms. Now from Ohm's law, we can calculate the current in the circuit. So the voltage of the battery is 6 volts. The total resistance is 410 ohms. So we get a current of 14.6 milliamps. As we've seen from a previous lesson, if 14.6 milliamps goes through the 105 ohm resistor, then 14.6 milliamps will also go through the 305 ohm resistor because they're connected in series, and current is the same in series. Okay, so starting at point A, and we'll move counterclockwise around the circuit. The first element we come across is the battery, and we go from the negative to the positive terminal of the battery. So the change in electric potential across the battery would be a positive 6 volts. And then as we flow around, so we're starting from A, and we're going across the battery from the negative to the positive terminal. That's positive 6 volts. And then as we continue, we're going to go across this resistor. When we go from the negative to the positive terminal of the battery, that's an increase of potential. So we get a potential difference of positive 6 volts. When we go across the resistor, we're going to lose potential. Let's calculate how much we'll lose using Ohm's law. So the current is 0.0146 amps multiplied by 305 ohms, and that gives us negative 4.45 volts. So we have a potential difference of negative 4.45 volts across the 305 ohm resistor. Now let's calculate the potential difference across the 105 ohm resistor. Still using Ohm's law, we use the resistance and the current to get a potential difference of negative 1.53 volts. That was across the 105 ohm resistor. And then we arrive back at point A, which is where we began. So let's add up all of those potential differences. We had a positive 6 across the battery, and then we lost 4.45 volts across the 305 ohm resistor. We lost another 1.53 volts across the 105 ohm resistor. So we're going around one complete loop of the circuit, and we started with the battery. We had a positive 6 volts potential difference across the battery because it's providing energy to the circuit. We lost 4.45 volts when we went across the 305 ohm resistor, and we lost 1.53 volts when we went across the 105 ohm resistor. If we add all of these up to our measurement sensitivity, it's approximately 0 volts. This is consistent with Kirchhoff's loop rule, which says that the sum of the changes in potential around a closed circuit must be 0. Since electric potential is electric potential energy per unit charge, potential difference is proportional to change in potential energy. Since the sum of the change in electric potential is 0, the sum of the changes in potential energy also would be 0. This is consistent with the law of conservation of energy. Let's check Kirchhoff's loop rule with our electrical circuit. We'll use the same series circuit we just used a moment ago. So let's measure the potential difference across the components of our series circuit. First, I'll measure the potential difference across the battery. 6.26 volts. Now let's measure the potential difference across the 305 ohm resistor. 4.65 volts. Now we'll measure the potential difference across the 105 ohm resistor. 1.607 volts. So if we add the two readings across the resistors together, we get 6.26 volts. And when we measured the potential difference across the battery, it was 6.26 volts. So you can see that we get the same result as we did with our water circuit. Across the battery, the potential increased by 6.26 volts, and then the potential decreased step by step across these two resistors, a total drop of 6.26 volts. So the sum of the changes in electric potential around one loop is 0. Now you're going to use a simulation to answer some questions about circuit behavior.